Okay, so today we're going to focus on IA221. Let's focus on photo sensors. This presentation is a few years old and it doesn't contain the latest and greatest stuff. Photo sensors, especially vision systems, have continued to drop in price, continued to become incredibly more powerful. And I'm going to have to update this presentation. In fact, I'm probably going to have a complete separate lesson just on vision systems out there, because they are getting cheaper and getting better. And those are making it possible to do amazing things with automated machinery these days. So we're going to focus on some of the more tried and true old school vision sensors out there. And so here we are. Let's talk about them. So to begin with, let's just remind everybody of some basic terminology. And one of the first terms we learned in the sensors class is the term transducer. It is a device that converts one energy to another energy, usually in the form of an energy being converted to something I can use in my system, my PLC or my computer of some sort, that's proportional to the input. So output for most transducers in the form of electrical energy, because most PLCs have some sort of electrical input. And the example they give here is a loudspeaker is transducing from electrical energy to sound energy. That's an example transducer, but in our sensors world, that's probably not the most common one. So a sensor is a transducer that's used to make a measurement of a physical value, and it's a device that responds to a variety of things and converts it to electrical energy. So this is basically just sort of a reintroduction of some of these key topics. So let's talk about photocells. A photocell is the simplest form of light energy converter. A photocell is sort of considered a primitive PV photovoltaic cell. It can convert a light energy to electrical energy, and it's usually proportional. Like if I have a lot of light, I get a lot of voltage. If I have a little bit of light, I just get a little bit of voltage. So a photoelectric sensor is a special kind of semiconductor that uses some form of transmission or receiving of light energy and converting that to an electrical signal. It's a very generic term. So photoelectric sensor is sort of an old-fashioned term, but it's a very generic term. And theoretically, even a camera system would be considered a kind of photoelectric sensor, though of course way more complex and way more powerful than some of the simple primitive photoelectric sensors. Okay. Photoelectric sensors are often infrared. They're often measuring wavelengths of light that you can't see with your eyeball, with our primitive vision systems that are purely visual. And there's a huge spectrum out there that we can't see, obviously. And so sensors often are designed to send and receive light in infrared spectrum. In fact, infrared is probably the most common. Now, why would I use a photoelectric sensor versus a capacitive or inductive sensor? And that's because I can use a photosensor that'll shoot, 10, 20, 30, 100 feet or more and detect if anything's in between there. And they're used very inexpensively in garage doors. For instance, I can have an inexpensive garage door sensor that bounces across the entire width of a very large garage door and knows if somebody's dog runs through that gap and triggers that door to stop coming down. So it's a very powerful device. Obviously, it doesn't work very well if it's an extremely dusty, misty, foggy, or other kind of particulate environment. But it works pretty well, even in a garage with all the dirt, dust, and grime and, things you get in a garage, including exposure to the outdoor, environment on a regular basis. So they are pretty sturdy and can handle a lot of different systems. They're also relatively dropping in price. So when we get to photoelectric sensors, we're going to be looking at a few different kinds. And the three modes are through beam. In other words, I've got a sender and a receiver. They're two separate objects. My sender is basically just a fancy flashlight, right? I give it two wires to power it, a plus and a minus. It powers it up and it sends a beam, an invisible infrared beam, and that's all it's doing. And sorry, I'm just checking the messages. And then you have a separate device, which is your actual receiver. That could be 20 feet, 100 feet away. And we're going to be experimenting with one of those in the lab. We also have something called reflex/retroreflective. In other words, I can have a little light in one side of my sensor, little flashlight, a little emitter, built into the same sensor as a receiver. And when something comes up to it, the light bounces off and tells me that you come up to something. And we also have proximity diffuse reflective detection. So one of them can handle a direct beam bouncing off. You're a lot better with a mirror on the other side, or even better, a special reflector mirror with the, that was in my quiz, I forget the name of it, the little reflectors with the right angles built into it. I'm blanking out. Who got that question right in the quiz? You can tell me later. But yeah, using the reflectors with the design built into them, so any light going into the reflector bounces off at the same angle, you can use the retroreflective model. And you also can have diffuse model, diffuse proximity, just detect anything as long as it bounces light in that range. And you can tune the diffuse models so that they only pick up light in a certain spectrum. And we've got one of those in class, so you'll be able to program it. So let's go look at what the presentation talks about this. So generally speaking, an LED is used for most of these devices, and they emit usually invisible infrared light. Very few visible light sensor systems that I've seen out there. They say visible LEDs are used for retroreflective applications. Back in the old days, remember those when you watch TV and someone would be trying to avoid alarm system and they would spray like hairspray and you see like a red light, crossing the path. And that red light told the super spy or the thief or whoever it was that there was an invisible beam there that would be triggered if they crossed it. That doesn't happen anymore. Now those beams are completely invisible. They're infrared. You would need special glasses to see them in the infrared spectrum. So red LEDs are very uncommon nowadays for any kind of sensors. Generally speaking, you turn on and off the pulse on and off. They modulate. And by pulsing on and off very fast, they reduce the amount of energy they use and also increases the lifetime of the LED. And it gives you a pretty good signal. Theoretically, even more than all on. And I'm not sure how that technology works, but that's what this presentation says, and I believe it. Also, this is another key fact. By modulating the frequency of your pulsing, if somebody shines another infrared source that's not using that same pulsed modulation, it's ignored. You're only going to pick up the light beams that are pulsed at the frequency that you know it's being sent. So this keeps that thief or whoever it is from cheating somehow and putting his own pulsing regulator, unless he knows exactly the name brand of the sensor he's cheating. So all sensors have some number of these kind of components in here, but an LED sensor has, basically a photoelectric sensor has a transmitter and a receiver built into it. So you got the LED, which is your transmitter, and then you got the receiver that receives back that reflected light and converts it to a signal, and then you have an amplifier basically that transmit the information to some other source, like your PLC. So they take that generated pulse light and they convert it to an electrical signal. Typically through beams look like this, where you have a sender and a receiver, emitter and a receiver that are used, and any object that breaks that line detects an object. So they're digital on or off, they're not analog, right? Through beam have very, very long range. The effective beam is considered that within the cone of each one of those emitters and detectors, that effective beam is simply the line drawn between the two. But both of those devices, both the emitter and the source and the detector, both have cones, so you can be slightly out of alignment and still do a good detection. Although, of course, you want to be in as alignment as much as possible. And we're going to be playing around in the lab with very long distances and see how we can just manually line them up and get those signals to turn on. So the through beam have the longest sensing range, highest possible signal strength, the greatest light-dark contrast ratio, and they're the best trip point repeatability. In other words, you want a robot to come pick up an object, you probably want a through beam detector to tell you that that object's precisely at one particular point. So there's some downside. You have to wire up two devices in many cases. If the object is too small, it doesn't do a good job of finding it. Sometimes it's difficult to align them precisely, and so forth. So these are all things you might expect if you're trying to shine a flashlight on another flashlight. So let's talk about reflex retro reflective detection. Basically, retro reflection tells me that when I'm getting, I have a sensor, I bounce off some sort of mirror. In this case, we talk about a reflector. That bouncing off, if I put something in between there, tells me something's in the way. This is traditionally how garage door systems work. They have a reflector on one side and then the garage door source and detector on the other side. It's easy to align it, right? They're very reliable. And it's easy to wire it. The presentation says a lot of stuff here. I'm not going to read through everything. And so the limitation is you must detect a shiny surface. And the retroflection, the reflectors they sell you, which are very inexpensive now, they're used all over, trailers and on the ends of your driveway and everything like that. So they're very inexpensive retroflectors. However, theoretically, a shiny reflector attached to a car could also bounce the signal back and give you a false detection. But chances are, if you're pulling a car in, it'll detect the side of the car a lot more and stop your garage door. So there's a chance for false positive. So the last kind of system is what they call diffuse or proximity reflective detection. So I have a smart enough sensor, when it sends out a pulse, it's not going to need a mirror or a reflector on the other side. It's going to bounce off of anything with color. And so it'll tell if that thing has reached close by to it, or to tell me that a certain color has been put in front of it. If you can tune it, you can program your sensor to pick up only a certain color. And it does that the same way as the reflective work, but it using higher tech in the sensor side of it, the receiver side of it, to know what the object is and judge based on the wavelength and the intensity whether it's a positive or not positive detection. These generally have relatively short range, and they can be a little bit fussy in terms of programming. And we're going to play around with them, and we're going to see how fussy they can be. The maximum range for through beam is the primary importance. This does not have anywhere near that. This is something that has to be very close. Very specific range, because if you have a very diffuse object with the wrong wavelength, but it's very close, it's going to look like it's generating a lot of energy, right? It may give a false positive, where if it's too far, we might get a false negative. So that exact distance has to be set for detecting using the diffuse reflective methodology. And that's all I want to go over. So we've learned about through beam, reflective, and proximity diffuse reflective. Those are the three methodologies. And we are going to learn about them physically in class. And you're going to play around with each one of them. And so one of the key things in class that I want to make sure you do is when you pick up these sensors, I want you to recognize which one is which by checking their data sheets. I want you to recognize that you might have a sender, you might have a receiver, if it's a through beam sensing system, and you should know that you need both of them to get that sensor to work. And we're going to play around in the classroom. We're going to have some fun. We're going to shoot down the hall to see if we can sense at the maximum range for some of these devices. So I'll see you in the classroom.